is less dense than the other stuff, right? And so it would look like we had less of a gravitational pull. So it would look like we are further away from the center of the Earth. So let's just do that because I get screwed up with pluses and minuses. So remember that gravitational force is proportional to 1 over r squared, right? So as r increases, let's do this, g, gravity decreases, right? So if we have rho, let's say average, drops, okay, that implies that the force of gravity drops. And if the force of gravity drops, that implies that r is essentially increasing, that we are further away from the center of the Earth. Whereas if the density increases, whereas if the density increases, the gravity will increase and the radius will decrease. We're getting closer to the center of the Earth. So, the crust, as probably all of you know, is less dense than the mantle. So, if we go to crustal thickening, we get a geoid anomaly that is positive. In other words, the radius is increasing. If we go to an area where the crust thins, we're going to get a negative gravity anomaly. If we go to a place where the mantle thins, we're going to get a positive gravity geoid anomaly. Where's a place where the mantle might thin? There's a really interesting article recently that came out about mantle variations. The mantle actually can change material properties. So under hot spots, the mantle is actually much more liquid and it's less dense. We can call it mantle thinning, or we can call this a change in the density of the mantle. And obviously we get a geoid anomaly that was positive. Obviously in areas where mantle is thicker, we're going to get a negative anomaly. And if we get the full lithosphere thickening, we're going to get a slightly positive anomaly in this case, assuming that the mantle thickness is increasing more than the continent. Okay, and look at this. We'll talk about this later, why the Bouguer anomaly is opposite to the height anomaly. Okay, let's look at one other example just to think about this in general. So, all of you know about subduction zones, right? So this is ocean crust. And then we have continental crust. Right? And then we have mantle. And asthenosphere underneath that. And they basically go down there. And this is continent. It goes on forever. What would we see in terms of a geoid height where the continent at this subduction zone? What do we have analogously at this picture? Exactly, we have a significant crustal thickening because not only is the continent thicker, but the ocean crust is less dense than the mantle. So we would expect a very high geoid anomaly on the continental side of subduction zones. And let's take a look. Okay, subduction zones, starting with Alaska. Subduction zone, the Andes. Subduction zone, Turkey and Greece. Subduction zone, Japan. Subduction zone over here in New Guinea and New Zealand. So most or all of these subduction zones have positive geoid heights associated with them, as we would expect. These are measured gravity values. Okay, this is what we've measured worldwide in terms of gravity. What other areas have positive geoid heights? Can you see the hot spots on here? Can you see where Hawaii is? Okay. Either mantle thinning or a change in mantle properties, probably. What about this thing right here? What is that? Pardon? No. Good answer though. That's actually, let's go to America, a map of America. So again, this is a gravity map. It's the geoid height, the geoid anomaly, relative to this ellipsoid across America. So that area that you're talking about is actually Yellowstone. Okay? You've seen all the pictures about Yellowstone being a supervolcano and actually having erupted over the years. Well, that area is associated with this mantle. That's less dense, yeah. Oh, the blue part, okay. That's actually associated with oceanic crust. So oceanic crust is more dense than continental crust. And so the geoid height is actually lower than it would be on the continent. And I'm not sure if it's zero or something negative. Okay, so Yellowstone is a hot spot, but like you were talking about, what's your name again? Kashaw, okay. Can you see these little lines that are coming through there? Those are failed rift systems. And those rift systems probably happened in the Precambrian in many cases. What about this one right here? Here's the Sierra. Well, we know that in the past, the Juan de Fuca plate was actually subducting beneath the Sierras, so obviously that would be a negative anomaly. And actually, the pull down here, the force holding down the crust, will create a negative anomaly in some cases. So on the other side of the subduction zone, you'll actually have a negative geoid height. What about up here in Hudson's Bay? Anybody know what that is? Why is that negative? Well, that's associated with the glaciers, the ice age. Basically, the glaciers push down the crust, the way the glaciers push down the crust, and it hasn't rebounded yet. It's still coming back up very, very slowly. Okay, I went through this pretty quickly, and I kind of assumed you guys knew a lot about plate tectonics. Who doesn't know about plate tectonics? You can raise your hand up, and we'll do a poll about it. Haven't heard of plate tectonics? We have? Okay. So we went really quickly through subduction zones and some of the plate movement over time. One of the other interesting things is, has anybody been up to the hot springs in Calistoga? Never? They're really great, mud baths and hot springs. Calistoga is right above San Francisco, actually, probably right up here. Now, what if you drew a straight line, roughly, between Calistoga and Yellowstone? What would you see? What would you find? Notice that Calistoga's hot springs, Yellowstone's hot springs. Well, you'd actually see that there are an awful lot of hot springs along that line. And as a matter of fact, what's associated with hot springs? Well, hot spots for sure. What valuable thing is associated with hot spots? look at units of gravity. So, rather than looking at it in CGS, CGS or MKS, I can't remember, but let's look at it in centimeters per second squared. So gravity is 978 centimeters per second squared at the equator, roughly 9.8. We define a gal to be 1 centimeter per second squared. Gal stands for Galileo. 1 milligal, obviously, is 1/1000th of a gal, which is about 10 to the